Assalamualaikum warahmatullahi wabarakatuh and good day. Okay, today I want on chapter 3, basic equation in fluid mechanics. Okay, at the end of this chapter, students should be able to understand and analyze basic equation in fluid mechanics and list out and also apply Bernoulli equation and momentum equation. Okay, for introductions on chapter 3, so we look at the classification of types of flow. Incompressible fluid flow is assumed that the fluid has constant density. How liquids are slightly compressible, we usually assume them to be incompressible. Okay, so with a steady flow means steady with respect of time. So all the properties of the flow at every point remain constant with respect to time. So for the uniform flow, happen when the cross section with shape and the area through which the flow occurs remain constant. Okay, but for the path line, is the trace made by a single particles over a period of times. So look at this is the path lines shows the direction of the velocity that to the point of D and point of the B here, direction of the path line. Okay, flow rate and means velocity. Okay, the flow rate and means velocity known as the quantity. Okay, means of the quantity of fluid flow per unit time across any section. The flow rate can be expressed in terms of volume flow rate. Okay, volume flow rate with units meter cube per second, mass flow rate, and with unit of kg per second. And this is the equation for the mass flow rate. And C weight flow rate with unit of kilonewtons per second. And the equation of G, K weight flow rate is equal to specific this one times by area times by the volume here. Okay, so we can conclude that the operation of the flow rate to get the velocity or the volume, sorry, for the velocity here, sorry, the V is the velocity is equal to Q is discharge divided by area is also equal to the mass of flow rates by of the density times by area and the weight of the flow rate. Okay, example 1. Okay, the velocity of liquids with the specific gravity is equal to 1.4 in a 150 mm pipeline is 0.8 meters per second. So calculate the rate of flow in liter per second, meter cube per second, kg per second, and kilonewton per second. So we use the equation of the discharge of flow rate. Okay, so the Q is equal to A times by the V. So use the area of the pipeline, pi times by 0.075. Okay, because this is the pipeline diameter, so this is the radius. So you get the Q is 0.01414 meter cube per second. So from this, you convert that per liter per second. We know that the 1000 liter is equal to 1 meter cube. So you convert to liter per second. So you get this value. Okay. And for solutions for the using the mass flow rate, so you just use these equations and you get the value of this one, and also use these equations for. So continuity equation. Okay, the mass of conserved when a fluid is in motion. So consider a one-dimensional steady flow of fluid through a pipe. So the flow is from this pipe at the point 1 here to the point 2 here. Okay, so the mass are the continuity equations. So the flow is flow from this pipe to this pipe. Okay, the point 2 here. So the principle of mass conservation is in over A1 goes out to A2. So you will get the is okay. So this okay, this is the called the continuity equation. Okay. A1 is equal to V1 is equal to A2 equal to V2. Okay, this is using the continuity equation. Okay, for the steady flow, so using the okay mass flow rate, so this is the continuity equation for the this one control on volume, and for the using this one, so we use this one. Okay, the steady flow. Case incompressible flow with density constant for both steady and unsteady flow. So we also use the same equations using the continuity equation. A1 times by V1 is equal to A2 times by V2 is equal to Q, flow rate. Okay, example 2. Okay, water flows in a river at okay, the flow past bridge A1 is 37.2 meter cube per second. At the same instant, the flow past bridge 2 is 26.9 meter cube per second. So at what rate? Okay, what is the flow rate? Is water being stored in this river between the two bridges at this instant? Okay, so this is the solutions here from point 1 to the point 2, from the bridge at the point 1, bridge 1 to the bridge 2 here. Okay, so Q or Q1 minus by Q2 is equal to dV over dt. Okay, because this is the change from the velocity over the dt. So we get the Q1 minus by Q2. So you get dV over dt, you get this value. Okay, example 3. A jet of water discharged into an open tank and water leaves the tank through an orifice in the bottom at a rate of 0.003 meter cube per second. If the cross-section area of the jet is 0.0025 meter squared, where the velocity of water is 7.7 meter per second, and what rate? Okay, what is the flow rate? Is water accumulating in the tank? Okay, so this is in flow. Okay, net of outflow Q out minus by Q in. Okay, inflow into control volume, and this is outflow from control volume, so the positive using this this equation. Okay, actually this is times by because in Q in they give you the area area of the water leaf through an orifice, so you must times by the velocity here, so you get the Q in here. So that's why you get this one, and you get the value of the Q net is negative here. Okay, so negative sign shows alkalinity of water in the tank. Okay, shows alkalinity of water in the tank here. Okay, example 4. The river discharged into the reservoir at a rate of 400,000 meter cube per second, and the outflow rate from the reservoir through the flow passage in the dam is 1. So if the reservoir surface area is 40 kilometers squared, what is the velocity of water rise in the reservoir? Okay, this is actually the reservoir here. Okay, this is the dam here. Q rise. So Q out is equal to Q in, okay, for the continuity equations. So Q out minus by Q in plus the Q rise here. So you get the 0. Okay. So you get the Q rise is this value, and we know that the V rise is equal to Q rise times divided by area. So you get the value of the velocity of water rise in the reservoir is this value. Okay. So we look at the energy equation. So in chapter 1, in chapter 3, we discuss about the continuity equations, and then we discuss for the energy equations. Okay, consider frictionless steady flow of an ideal fluid along the streamline. Okay, along this streamline here. Okay, shown below, we shall consider the force acting in the direction of the streamline. Okay, acting of the streamline here. So we shall apply Newton's second law, that is using the F. Okay, force is equal to ma. Okay, the cross-sectional area of the element at the right angles here, the streamline may have any shape and vary from A to A plus over the change of the area of this steady flow. Okay, kinetic energy with a fluid of mass m with all particles moving at a velocity v possesses a kinetic energy. Okay, so the kinetic energy, so this is the equations for the kinetic energy. So for unit weight, so we use the weight here, unit in meter or feet. Okay. Okay, so potential energy using this potential energy per unit mass. Okay, this is per unit weight and this is per unit mass. Okay, potential per unit volume, so you get this. Okay, pressure head. So a particle of fluid has energy due to its pressure above the term. Okay, so pressure is equal to this one, equations. Okay, pressure head. So you just rearranging this equation, so you get the energy per unit weight. Okay, based on, okay, so you get this Bernoulli equation theorem. Okay, so this is the Bernoulli equations. Okay, basic assumption. So the viscous particle friction effects are negligible. Flow is steady, applies along a streamline, fluid is incompressible, and no energy is added or removed from the fluid along the streamline. So just remember this equation for the Bernoulli theorem. Okay, for the H, okay, pressure head is equal to density, P pressure, okay, the pressure plus the Z here and the this one. So this is the Bernoulli theorem. Okay, for the case of incompressible fluid with the specific weight constant, so we use this equation. Okay, energy per unit weight. Okay, this is energy per unit mass. Okay, and this is energy per unit volume. But the usually equations that we always use is this equation. Okay, energy per unit weight. Okay, considering Bernoulli's equations at point 1 to point 2, so you must use these equations. This is called the Bernoulli equations when the flow through point 1 to point 2. Okay, remember these equations. But in your exams, so this equation will be given. So no need to worry. Okay, so example 5. Okay, so glycerin with specific gravity 1.26 flows in the pipes at a rate of 700 liter per second. So at point 1 here, okay, this is point 1. Okay, point 1. The pressure is 300 kilopascal. Find the pressure at point 2 here. Okay, if the elevation point 2, okay, the elevation is 1 meter. Okay, from the point 1 to the point 2 here, so the height of the elevation is 1 meter. So neglect head loss value. Okay, so first step, so you must find the velocity at point 1. So you use this equation to get the volume, the velocity 1. Okay, velocity 1 is equal to Q over A1. So you get the velocity 1 is 2.476 meter per second. And then you find the velocity 2 at the point 2 here. So you get the V2 is 9.903 meter per second. Okay, because the Q is given as 700 liter per second. So you just convert to meter cube per second. Okay, considering Bernoulli's equations at point 1 to point 2, so you must write the equations of the Bernoulli. This one, point 1 here. So this is point 1. Okay, this is at the point 1 here. Okay, equation at the point 1. And this is equation at the point 2. Okay, HL is the head losses. So in this case, in this questions ask you to the neglect head losses. So HL is no need to calculate. Okay, so you just put all the value here to this equation. So until you get the P2 pressure at point 2 here, so you get the 254.4 kilopascal. Okay. Okay, example 6. Water at 10 degrees Celsius flows from section 1. Okay, from the section 1 here. Okay, from the section 1 to the section 2. Okay, from the section 1. Okay, from the section 1 to the section 2. Okay, so this is the velocity head for the point 1. This is the velocity head for the point 2 here. Okay, specific weight. So we know that 9810. D density for the at point 1. Diameter at the point 1. And the pressure 1 here. V1, 3 meter for the velocity 1. Diameter 2. So we know that the height, the difference height from the point 2 to the point 1 here, the elevation head. So Z2 minus by Z1, so we get the 2 meter. Okay, we know that using the continuity equation, this is called continuity equation. Okay, Q is equal to Q1 is equal to Q2. So A1 times by V1 is equal to A2 times by V2. From this equation, continuity equation, so you can get the velocity 2, the value of the velocity 2. After you get the velocity 2, so you must use the Bernoulli equation here. Okay. Step 1, so you must use the continuity equation. And the step 2, so you must use the Bernoulli equations. So just put all the value here at these equations. So you get the pressure 2 is 329.6 kilopascal. Okay. So you look at example 7. Also find this example also to find the energy losses in this system, to get the flow rate through the siphon and the pressure at point B, point C, okay, point B, point C, point D, and point E. Okay. So figure shows a siphon that is used to draw water from a swimming pool. The pipe that makes up the siphon has an inside diameter of 40 mm and terminates with a 25 mm diameter nozzle. Okay, this is the nozzle here, 25 mm nozzle. Assuming that there are no energy losses, so no energy losses, so HL in the system, calculate the flow rate through the siphon and the pressure at point B, C, D, and E. Okay, first step, okay, find the flow rate of the pipe by equating the total energy at point A, okay, at the point A here, okay, and the point F, okay, point A at the water level here, okay, point A and to the point F. Since the pressure at both locations are known, so we use the Bernoulli equation here, okay, from this, okay, the level here to this level here. So we get the Bernoulli equation. Okay. So gauge pressure at A and F are 0 because this is atmospheric pressure. Okay, because this is atmospheric pressure and also the atmospheric pressure. So PA is equal to PF is equal to 0. Okay, so the elevation head of the ZA to the F here is 1.8 times by 1.2, so you get the 3 meter. The velocity in the tank is negligible as it is small compared to velocity in VA. Okay, this one is equal to 0, VA is 0. Okay, so therefore using this Bernoulli equation, so you just insert all the value that you find. The P, A is atmospheric pressure is 0. Okay, don't have this one. Okay, VA also don't have, and the F also 0. So ZA minus by ZF is the 3 meter. So you get the 3. So this 0 plus 3 plus 0 is equal to 0 plus the VF squared over 2G. So you get the velocity at F, this value. So we know that the Q is equal to A times by V. So you get the flow rate in this siphon. So you get the flow rate is this value. Okay. After we know that the velocity the velocity F, so we want to find the at point B, point C, point D, and the point E here. So we know that the VB is equal to at the VC is equal to VD. Okay, so we get the velocity B, velocity C, D is the 3 meter. using this equation. Okay, so energy equation between A to B here. So you use the Bernoulli equation from the point A to the point B here. Okay, so point A is 0 because this is atmospheric pressure. Okay, so and the Z, okay, Z to ZB because they have, okay, ZA and the ZB, so still, okay, don't have the difference between the point. Okay, so the ZA minus by ZB is 0. So VA also, this is also 0, 0, and 0. So we just have the pressure at B and pressure of velocity B here. So you get the pressure at B because we know that the VB is 3 meter per second. Okay, so look at the energy equation between A to F, sorry, A to C, A to C. Okay, so also use the Bernoulli equation, okay, using the pressure A to the pressure at C here. So you use this one. Okay, Z A to the C here, okay, is negative 1.2. Okay, VA, this is 0, 0. Okay, so and also the VC here. So you get the PV, this value. Okay, one more thing, you must remember this equation step by step. So you must know the Bernoulli equation. Okay, so step by step you must know the pressure at A and pressure at this point, every point. So you must do the Bernoulli equation here and calculate the pressure using this equation. Okay, so example 8, also to find the, okay, also find, so these questions to find the friction head loss. Okay, so if H is equal to 0.5 meter and the pressures at A, so point B to point A here and B are 170 and 275 kilopascal respectively. Find the direction of flow and the pipe friction head loss in meters of liquid. So assume the liquid has a specific gravity. Okay, so use the Bernoulli equations from the point B to the point A here. Okay, so the point B and the point A here. So you just put all the value here. Okay, so you get the HF because you want to find the pipe friction head loss in meter of liquid. Okay, so you get the flow from B to A is negative. Okay, that's why you get the flow from B to A is negative because we assume that the flow is from A to B. Okay, first before you calculate, so you assume that the flow is from A to B. Okay, you assume that A to B. That's why when you assume that A to B, so you get the negative. Okay, so if you get the negative, the real situations is B to A.